Welcome to a new lesson of the Haskell course. Today we will learn about the Monad type class and how you can use it. This lesson assumes you saw and understood all the lessons up until now and that you did your homework. Especially lesson 11 about basic I/O, lesson 18 about Functor, and lesson 19 about applicative and effects. This lesson is easy in comparison. So, if this lesson feels too hard, you need to review those first. We'll start with why monads to begin with. Then we're going to extract the pattern for maybe, either, and log. We'll use those patterns to generalize to the monad type class, explore the abstraction monarchy, the monadic laws, how monad is defined in base, and finally, the do notation. So, why monads? To understand why we need the monad type class, we first need to see the limits of the applicative type class. Let's say we're working on the backend of an app that requires users to sign up, and we have to validate the values somehow. Here's an example of a data type for a user. We have the user with a single constructor that contains the fields for the name, the password hash, and the user's email. Everything as a string. So let's run this. And here are a few dummy functions to validate the value. So we import some helper functions from the data char module. We normalize the username. So we take the username and we make sure first that contains at least 3 characters. Then we check that all characters are alphanumeric or underscore. And if they are, we map to lowercase everything in the name. Now we have a normalized username. Then we check the password, and if everything goes all right, we generate the password hash. So first we check that if the password has less than 8 characters, it's an error. Otherwise, if we have at least one uppercase letter, at least one lowercase letter, and at least 1 digit, all good, and we hash the password. In this case, we avoid the function to hash the password. This is just a dummy function, but in a real implementation, this part should properly hash the password. And finally, we'll normalize the email. So first we check if the email string contains the @ sign, and if it does, we map to lower the email. So we have these helper functions, and of course, these functions should not be used in production code. The important part is not how they are implemented, but how do we use them. Now let's create a function that takes the username, the password, and the email and creates a user if everything is okay. So we have the create user function that takes, as we said, the username, password, and email. First, it's going to normalize the username. Then it's going to check and generate the password hash. And finally, it's going to normalize the email. If everything is all right, we are going to apply the user constructor to the 3 final values. So let's run create user so we have it available. But wait a minute. We did a lot of work in the previous lesson to define the applicative type class precisely so we could easily deal with this. Applicative allows us to apply a regular function, in this case the user type constructor, to 3 values at the applicative level, in this case the either e values for each of the helper functions. So we can simplify the function by using the apply operator like this. Much nicer. Now we can clearly see that we're creating a user by applying its constructor to values that result from running the possibility of failing effect, either E, of normalize username, check and generate password hash, and normalize email. We know that these two should return the same value, so now if we run, we'll see that for every case, the function that we run using the applicative operator returns the corresponding value. And if we provide the same value for the function without the applicative operator and with the applicative operator, we see that they return the same value. We knew all this from the previous lesson. If it didn't seem obvious to you, you might want to review the applicative functor lesson. If it made sense so far, let's make the code slightly more realistic. starting by changing the user type to this user account type. Now let's run this. As you can see, we use a few type synonyms to help with readability, and we change the fields to more realistic ones. We have user ID that holds a unique ID generated by our backend, which will never change. We have the username field that holds the unique username chosen by the user, and that it could be modified in the future. The user pass hash that holds the user's hash password to verify its identity when they log in. We have user email that holds their email, and the user has enterprise Boolean flag, indicating if the user is part of the enterprise plan. Now we'll create 6 dummy functions to validate all these fields, same as before. So here are the first 3. We have the normalized username that does the same as before. We have the check username available. In this case, takes the username, and in a real implementation, we'll check in a database if that username is available. And finally, we have check and generate password hash that is the same as before. We're doing 2 things to reduce the noise around the point that we want to make. So one is that we use maybe instead of either to avoid all the strings explaining the errors all over the code. The second one is that in some cases, we will have to use IOFX, for example, here to connect to a database, but we also ignore this since it's irrelevant to what we want to learn. As before, the actual implementation of these functions don't matter. What matters is how we use them. Let's run this so we have them. We have the other 3, generate user ID, in this case, it's just a hard-coded ID, and in a real implementation, you should generate a real ID. We check for the enterprise plan, which in this case, first check that the @ sign is inside email, and if it is, we remove everything before the @ sign and check that the domain of the email is enterprise.com. And finally, we simulate a database insertion. So we have the insert user into database that takes all the final values that we need and creates a user account and returns just the user account if it's successful. Let's run this. Okay, we have all the building blocks we need to write our own register user function. Same as before, let's see how it looks dealing with effects manually. So this will be like the whole thing. Let's run it first and let's explain it. So the register user function takes the name, the password, and the email, and it first normalizes the username, then checks if that normalized username is available, then checks if the password is weak and generates the password hash if it's not. Then we generate a unique user ID, then we check if the user is part of an enterprise plan, and after all that, we insert the user into the database and return it. This function looks a lot like create user. Pause the lesson and try to simplify it using applicative operators, the same way we did with create user. Then come back and we'll do it together. Okay, could you do it? What issue did you encounter? If you actually tried, you might have noticed a small but key difference between the create user function that we could greatly simplify using the applicative functor and the register user function we couldn't. And that is, unlike with create user, where all actions are independent and the results are used all at once at the end, in register user, we use the results of some actions as inputs to other actions. For example, the check username available function takes as an input the result of running the normalized username effect. It turns out that using the result of one action as an input to another action is very common, but we don't have an abstraction to deal with this yet. Don't worry. We just have to do the same thing we did to extract map, functor, applicative, and all other abstractions we extracted so far. We identify the repeating pattern, extract it, and use the abstraction instead of writing the whole pattern. So let's extract the pattern for maybe. Now, instead of following the slides, I'm going to do it in the code so it's easier to follow. So let's copy the code that I told you earlier. Let's open it first. Example.hs, and we paste the code. So we import data.char here in the first line. Then we have the user account types, we have the types, we have all the functions we just talked about before. We have the main function, the register user function that we had before. And we have the register user prime that you should have tried to simplify the register user using applicative functor. But now, instead of trying to use previously abstracted patterns, we're going to abstract this pattern from scratch. So let's go to the register user function, and we see that there's a clear pattern that repeats all the time. We have a case expression for something that results in a value that then it's used by another case expression that results into something that has a value that is used in another case expression. So the case expression is the repeated pattern. So we're going to copy this and move to the bottom, and we are going to call this bind maybe, because we are going to be binding maybe values. And we're going to say equals to the thing we just copied. Awesome. So let's center this. And let's see. So we have an arrow down here, but that's because here we're just opening a case expression without finishing it. So let's plug this type hole using undefined. Okay, so now we have variable not in scope, uname. That's because we want to generalize this whole expression into like any expression that it gets executed and that passes the value to the rest of the function, which is what's happening on top in the previous function. So let's rename this. Let's say, okay, instead of this specific action, we want any generic action that is of type maybe A. So we can just call it maybe A. And it's going to complain because this MA value is not in scope. So we have to provide it as a parameter. Now it's happy again, but we still are undefined here. Before dealing with this undefined, let's generalize this result name. Let's say val for value. So this value is going to be of type A because the case expression is for a maybe A type. So the case that is a just value of type A. And so now we remove this undefined and we have to deal with this. So what we see in the previous function is that, for example, here for a normalized username, we return the norm username and we use it in the rest of the function. If you see for this path of the case expression, this whole thing is the continuation, the rest of the function. And for this case expression, this is the rest of the function. So everything that comes below is the rest of the function in this case. So I can just create a variable that represents the rest of the function, the continuation of the function. So let's call it cont or continuation. And of course, we don't have the scope, but one thing that we know that this continuation function will have is the val value of type A. This val should be available inside this continuation function. That's the point of it. So the only way to have this value inside the body of continuation is to provide it as parameter. So we provide the value as parameter, and now we have an error and a hint. The hint we can ignore, so it doesn't bother us anymore. And we still have the error that variable not in scope. So we have to provide the continuation function as a parameter. And that's it. We extracted the pattern. Now we have to use it. So let's see. So we're going to copy this whole thing. Come below, paste it, delete the undefined. So far, so good. And now, how do we replace it? Okay, so we can identify the action that we want to evaluate. And the continuation that we want to provide the value to. All we need to do is, for example, we could say bind maybe, and of this normalized username action. And in this case, we remove the pattern that we are replacing. And here we know that bind maybe is going to provide the result of evaluating the normalized username applied to uname. So we need a way to capture the result and provide it to the rest of the function, to the continuation. To capture that value, we can just use a lambda function. So we can turn everything that comes after the bind maybe, we can transform it into a lambda function by just open brackets, creating the lambda function that it used to be named norm uname. So let's call it the same. Norm uname. And the body of the lambda function is everything that comes after it. So it's going to have an error because we need to close the parentheses. And that's it. We replaced the first occurrence of the pattern with bind maybe. One thing that I'm going to do now to make it more readable once we finish is to move the bind maybe from being an prefix function to being an infix function. That way, we can clearly separate the action that we're evaluating and the continuation. So we're going to put the bind maybe here, and we're going to remove it from here. And we don't need the brackets anymore. And now we can do the same thing for all the other cases. So let's delete. Maybe we create a lambda function. In this case, we don't use it. So this is a special case where we ignore the result. We just need the effect to be positive instead of failing. So we can just ignore and remove this, close parentheses, come back, and we can do the same thing all over again. So we don't need this anymore. We can bind maybe. We can name it pass hash, same name as before. We remove this and we close parentheses. And we keep doing this until we are done with all the scenarios. I'm going to speed up the recording so it's not boring. Okay, so we replace the pattern with bind maybe in every scenario. And this is a little bit hard to read, so we're going to align the bind maybe so it's really nice to read and comprehend. There you go. Perfect. This is significantly easier to read. On each line, the first argument is the function we're evaluating, and the second is the rest of the code. We use lambda functions at each step to capture the resulting value as a parameter and provide the rest of the code as the body. And that's it. We are done extracting the pattern and replacing it in the code. The part that handles the errors is hidden inside the bind maybe function. We'll return to this, but let's do a couple more first. We're going to go back to the slides so we can make it faster. And in the slides, you have available all the steps that I just performed in the code. Here is when the bind maybe function is used as a prefix. And here is when it's used as an infix. And now, for completeness, let's do the same for a register user function that uses the either E type. Let's start by redefining the helper functions. So here are the first three. They are the same three: normalize username, check username available, and check and generate password hash functions that we had before, but now they use the left and right constructor because they return an either string type. And here are the other three. Let's run this. Generate user ID, check for the enterprise plan, and insert user into database. Now that we are finished with the boilerplate, this is the new register user function with arguably better errors. So let's run this. And based on what you know now, pause the lesson and extract the pattern in a function called bind either. Okay, hopefully you arrive to something like this. This is the bind either function that takes an either string a as a first parameter, either a, and a function that takes the value of type a and returns an either string b, and then it applies this function to the result of the first action and returns either string b. As you can see, the implementation is rather simple and pretty much the same as the bind maybe function. Now, pause the lesson again and replace the pattern with the infix bind either function. Done? You should have something like this. Let's run it. As you can see, we reach out pretty much the same register user function with a small difference that the name is bind either instead of bind maybe, and the resulting value is of type either string user account instead of maybe user account. But otherwise, the body of the function is the same as before. So far, so good. Let's do one a bit different. Let's say we have a data type that contains the result of a computation plus a log that contains an explanation related to that computation. One possible implementation could be this one. So let's run this. We have the log a data type, which has one single constructor, also called log, and it contains a list of strings and the type a. Now we create the add function that takes two integers and returns a log of int. And this add function logs that it adds the first value with the second value and then performs the action. So if we add 4 and 6, we get 10. And if we add 3 and 7, we also get 10. But in both cases, the logs are different. In the first case, we added 4 and 6. In the second case, the logs said that we added 3 and 7. In both cases, the function returns 10, but the inputs are different. We wouldn't know the difference if there weren't for the logs. And whenever something breaks, you really want to have logs. I should point out that this is a highly inefficient and hard to use type, so don't do this if you want to add logs to your production code. However, it will be simple enough to use it as a tool to learn monads without much overhead. Okay, so for the sake of this lesson, let's change one more time the original example to use log. To avoid complicating things, we'll assume the functions cannot fail anymore. You will learn how to combine effects in the future. So our first three helper functions now look like this. As you can see, the logic inside the function never fails. Instead, it keeps going, but it logs what was wrong using the string. So if the length is less than 3, we log that the username is too short and provide the username, but we still perform the function of normalizing the username. Of course, in a real implementation, you will have both the effect of logging information and failing. As in the first two examples, what matters is not these definitions, but what we do with them. So let's run this and let's go to the other three. Same as before, we log instead of failing. Now that we have the boilerplate out of the way, let's do the interesting part. This is how we can handle the effect of logging by hand in our register user function. Notice that the pattern is similar to the previous one, but with one important difference. The results, for example, norm username, passhash, user ID, etc., are binded between functions as before. So norm username is used here, generate user ID, it's used here, etc. But the logs are accumulated at the end. As you can see, we have the logs in every step and we don't use them until the end. When we want to return the end result, we concatenate all the logs together. That will slightly affect the implementation, but the concept remains the same. Okay, so we see that we repeat the case and log lines 6 times and then have an extra log line at the end. Let's run this first and copy the final 5 lines. And it's a bit too big, so let's make it smaller. We just took the last 2 case statements at the end and named them bind log. Why use 2 case statements instead of just 1? Well, in the previous 2 cases, we could handle the errors independently one at a time. Even though the values were threaded and used between the actions, the effects were independent. This time, however, we need to specify how we will combine the logs. Not only the values depend on previous actions, but also the effects. So we need to specify how we will combine the logs, and we need 2 logs to do that, so we need 2 case expressions. Now let's generalize the first case statement. We can give the first log action the name L1. L1 contains the logs1 list of strings and val1 as a result. Now, how should we continue next? Right now, it's a super long function name with a bunch of parameters. But in reality, we can generalize this into a function that takes val1 as a parameter. We have already done this before and call it cont for continuation. So let's do that. The result of applying cont to val1 and evaluating the log effect generates a new log value that contains the logs2 list of strings and the val2 result. So let's change this. Excellent. So we run 2 log effects generating 2 log values. The first effect returns the value val1 that we provided to the continuation to generate the second value val2. Now, what we want is to make sure all our logs are present. So we'll concatenate them in the order they were performed and return the final value like this. Okay, we generalize the pattern here, but same as before, we are creating L1 and cont out of thin air. So let's provide them as arguments to get a final bind log expression. And we are done. We can explain the pattern by saying we take a log action and a continuation. We evaluate the action and provide the result to the continuation. Then we evaluate the continuation to get the final result and return it wrapped in a log constructor with the logs combined in the correct sequence. The only change with respect to the previous bindings is that we need to extract a bigger pattern to specify how to combine the logs. However, that's just an implementation detail. How we define the bind function depends highly on the effect that we want to represent. What stays the same is the type and meaning of the function. Now we can replace the patterns with the bind log function to get our final expression for register user. We run this. Perfect. We have all the logs. We did enough groundwork to present our first definition of the monad type class. If we zoom out a little bit, there are 2 things that we have accomplished so far. One is that if we take any of the register user definitions we had so far and change the name of the bind something to just bind, we completely hid the effects and only left the sequence of logical steps visible. This is an amazing accomplishment. The next person who reads the code will be able to focus on the logic of our function instead of dealing with the effects. On top of that, we generated 3 higher order functions that have the same interface and represent the same concept. You can clearly see that the interface is the same. A function that takes an action of type something A as a first parameter, runs the action to extract the value of type A, and applies the function provided as the second parameter to this value of type A to get a new action of type something B. In other words, we are binding effects by allowing the second effects to use the result of the first effect, something we didn't have an abstraction for. This seems, and it is, a pretty useful concept. So we'll create a type class to represent it. here's our initial approximation of the monad type class definition. A monad is a type with an operator to sequentially compose two actions, passing any value produced by the first as an argument to the second. This is not the final type class, but it already encapsulates the concept of monad, and that's enough to define a couple of instances to have something to work with while we figure out the rest. Why do I use this weird symbol instead of something like bind m? Well, in all three examples, it looked better to put the bind something function as an infix function. So it's better to create this function as an infix operator from the get-go, same as with Applicative's apply operator. Using this definition, we could implement the monad instances for maybe either e and log like this. Having the name of the functions may be too much of an indirection, so let's replace the names with their bodies and simplify a bit to get the same instances. These are the same definitions we derived earlier, but with a few aesthetic changes. We are pattern matching instead of using case expressions, and we change the name of the continuation function from cont to k because that's the name we use as a convention. So for the maybe type, in the case that the first action returns a value, we apply the continuation to the value and keep going. In the case that it doesn't, we ignore the continuation and return nothing. Same for the either. In the case of the left, we just ignore the continuation and return the same value. In the case of the right value, we apply the continuation to the result and keep going. For the log type, we pattern match to extract the values of the first action, then we apply the continuation to the result of the first log to get the second log and the final value. Finally, we construct a new log with the log constructor, where the logs are the concatenation of the first log with the second logs, and the value is the final value. And with these instances, all definitions of register user will look like this. Now that we have a definition for monad, let's try to understand it better by seeing how it relates with functor and applicative. The relationship between functor, applicative, and monad has a clear hierarchy in theory and in practice. We won't discuss the relationship from the category theory point of view in this course because you don't need to know that to be an effective Haskell developer. But what you do need to know to be an effective Haskell developer is how these type classes relate to each other and which one should you use when. In the past, Phil Wadler discovered that the concept of monad will be helpful to sequence effects in our lazy language. We also knew that functor was a powerful concept. So, in the first Haskell report of '98, we had these two type classes, but they were unrelated. This diagram shows the hierarchy of Haskell type classes defined in the prelude and the types that there were instances of these classes in 1998. As you can see at the bottom, the monad type class has no dependency. Functor didn't relate to any other type class, and there was no applicative. On top of that, the function that these type classes provided were slightly different than the modern ones. Even though the details of how this evolved to the current state and how it will still evolve are interesting, for the sake of time, this is the overview. In 1998, the Haskell 98 report is presented. It contains the functor type class with one behavior, fmap, and the monad type class with four behaviors, bind, then, return, and fail. Then, in 2008, in their paper Applicative Programming with Effects, Connor McBride and Ross Patterson presented the applicative type class, which fills a conceptual gap between functor and monad by enabling function application within a context. In 2014, the applicative monad proposal was presented to reconcile the mathematical hierarchy, where every monad is an applicative functor, with the language implementation. The key motivation for this was to reduce code duplication, make Haskell more beginner-friendly, and achieve theoretical consistency. The applicative monad proposal added applicative to the prelude and made it a superclass of monad. Finally, In 2018, the monad fail proposal was presented to remove the fail behavior from monad. We haven't discussed the fail behavior, and this is something you will learn after learning monad. But we can say that the problem with having this fail behavior is that fail cannot be sensibly implemented for many monads, defaulting to error in those cases. As a consequence, you couldn't use the monad safely because it might error out unexpectedly. Okay then, you might ask, why should I care about the history of these type classes? Why not just tell me the current state and that's it? Well, because code doesn't magically update itself once we decide to change something. Things take time, and transitions that could potentially break thousands of projects and libraries must be done carefully. This means that you, the beginner Haskeller, might see things that don't make sense, assume there's a reason for it that you don't understand, and become frustrated. The reality is that most of the things that confuse beginners stop being confusing after learning the history behind them. The monad type class is an example. This is the current monad type class as defined in base library at the time of recording. As you can see, the m-type variable in monad m is constrained by the applicative type class. This makes sense since in 2014 we added the requirement that every monad is an applicative functor. Another thing that makes sense is the bind operator, since it's the function that represents the concept of the monad type class. It's all good so far. However, what comes next might be confusing for newcomers. You might remember the second operator from the I/O lesson. We call it the then operator. This operator sequentially composes to action, discarding any value produced by the first. The default definition highlights this by using the bind operator, but discarding whatever is returned from the previous action with a lambda function. But wait, what? We already have an operator that does that using the applicative type class, which is this one. The then operator is defined using the bind operator, so its implementation might differ. But we are creating a new operator for the same concept. To make things worse, we see that the last behavior, return, which we also remember from the I/O lesson, not only represents the same concept as lifting a pure value to the applicative and now monadic context, but it also uses applicatives pure as the default definition. Even the implementation is the same. What is going on here? Well, you guessed it. History is what's going on. Because we didn't have an applicative type class when monad was introduced, all behaviors related to lifting and sequencing were part of the monad type class. And now that we do have the applicative type class, we have a lot of repetition. Sadly, this is not the only case, but we're working on it. In 2021, the monad of no return proposal was presented. It aims to remove the return and then operators from the monad type class. However, this proposal is still in discussion to this day. Some like the proposal, others don't. Whatever is the case now or in the future, you now know the reason and use case of every behavior of the monad type class. But there's one question we have to answer for the current time being, and that is, which type class should I use if more than one will do? Due to the close relationship between these type classes, sometimes you can achieve the same thing with more than one. For example, if you want to sequence effects ignoring the values, you could use both applicative or monad. So which one should you use? Here's a diagram that might help. It's a stack of cylinders that clearly states the hierarchy between these type classes. Starting with Functor, we can see Functor as the base of this stack. Then we have Applicative. All applicatives are functors, so you need to be a functor before being an applicative. And then we have monads. We need to be a functor and an applicative to become a monad. So all monads are applicatives. Now, the volume of the cylinders matters because the volume means that more types can be instances of this type class. So you can see that more types can become functor, a subset of those can become an applicative, and a smaller subset of those can become a monad. Now, the higher you go, the more restrictive it is because your type has to comply with stricter rules, but the more power your type will have in exchange, as it's hinted by the arms. In general, you want to restrict your implementation as little as possible. So, unless there's a reason not to, you should prefer the less restrictive type. If further along the line you realize you need more power, you can move up the ladder. In other words, always use the least powerful abstraction that satisfies your needs. This will help you write more general and reusable code. Now, before moving into figure out the monad laws, let's do some quick mental exercises. What is the result of return 3 of type maybe int? Just 3. What is the result of the write hey string binded with a function that takes x and applies write to x concatenated with the exclamation mark? You got it? And finally, the same as before, but this time the first action returns a left instead of a right. Awesome. And what about this one? It's the reverse function that takes a boolean and reverse it. So if it's true, it becomes false. If it's false, it becomes true. And we just log reverse. So if we start by lifting the true value to the monad context and then bind to reverse twice, what do we get? Aha! What happened here? Maybe an either monad instances come out of the box, but we just came up with the log type, so we have to define the monad instance. You can see here that says no instance for monad log arising from a use of bind. And because of what we just discussed, we need the applicative instance to define the monad instance, which in turn needs the functor instance, so let's define them in order. This is the functor instance for the log type. In the case of log, the logs are part of the structure, so we only apply the function to the value. We also check that the instance follows the functor laws. So when we fmap the function f to this log, we just apply the function to the value and return the same logs. Then to check the laws, as you remember from a previous lesson, if the functor type class follows the identity law, it implicitly follows the composition law. So let's fmap the id function and then apply the id function to the value without fmap. So it should return the same. Let's run it and it returns true. Okay, so we have the functor instance done. Now let's do the applicative instance. For the applicative instance, we said that the log type represents the effect of logging. So to define pure, we need to produce a log value with no effect. What will be to produce no logging effect? In our implementation, we can provide a list of logs, but with no logs inside it. So no logs, no effect. That is it for the pure function. So for pure, we provide a log, an empty log. So we still need the value. The pure is going to take whatever is provided as a value and apply log of empty list to the value to get the final log. The apply operator is a bit more complicated. We pattern match to extract the logs and values of both structures, here and here. Then, because we know that the first value is a function that we need to apply to the second value, we just do that. So we take the value of the third function that we know it's a function, and the value of the second if we apply the first to the second. All good so far. But what about the effect? We could think of two obvious things. One is that we could keep the last log only, losing all previous logs. The other is to concatenate them in the order we evaluate them. Any other choice wouldn't make sense. Actually, the first one doesn't make sense, but we're trying to go step by step. So between these two options, the second choice will keep all the logs in the same order as the expressions were evaluated, which is the desired effect. So that's intuitively the best choice. And if you're not convinced it's the best choice, why not checking with the laws? If we check all our 4 applicative laws for the case of keeping only the last log, we will see, let me comment here And as you can see, this implementation just returns the last log. So let's run this. False, the last one. We see that our instance breaks the interchange law. However, if we concatenate in the correct order, which is the option that makes more sense, we'll see that we do respect the laws. Great. Now we can define the monad instance by defining bind like this. We already went over this definition. We just pattern match the first one to get the logs and the value. We apply the continuation to the value to get the second logs and value. And then we construct a new and final log, concatenating the first and the second and returning the final value. So let's run this so we have it available. And now let's try the mental exercise that didn't work again. What is the result of applying return true and binding to unireverse and binding again to unireverse? Think about it for a second. Perfect. So now we have run the not function to the value twice. So it's true, false, true. So it returns true again. And because we did it twice, we logged twice the action. We have a working instance of a monad for a type we just invented. Sadly, as with semigroup, monoid, functor, and applicative, not everything is reflected in the type class definition. So we have to complement it with a few laws. Monads have 3 laws that we must look out for when creating instances of the type class. The first one is the left identity law. Return is just a regular function equals to pure. A is any value, and k is the continuation function. So, lifting a pure value to the monad level and binding that with the continuation function is equal to directly applying the continuation function to the pure value. Let's see how this looks for all the instances we have worked on so far, starting with the maybe type. We have in this case 2 continuation functions, one where the function succeeds and one other when it fails, k1 and k2. We can see that the left identity law is respected in both cases if we run like this. And we can also evaluate this in our heads. And if we apply k1 to x, in this case 3, we get just 3 plus 1, just 4. And if we return 3, we get just 3, which bind to k1. The 3 is provided to k1, so we ended up applying k1 to 3. We get just 3 plus 1, 4. So it makes sense and it's obvious. Also, trivially, the same can be seen for the either E type. We have the case where it doesn't fail, the case when it fails, and we check for the same property. The 3 is the pure value, and in the case that we lift it, bind, and provide to k1 or k2, we'll get the same result that applying k1 or k2 directly to the prior value. So we run this, true, and in this case I evaluate k2, so it fails. All good so far. Finally, we can also check the law for our log type. In this case, we have a continuation function that we can just actually call k because we don't have another one. We have this continuation function that takes any number and adds 1 to it, as we can see here. However, it also logs its action right here. Since return is just pure, which we define as equal to an empty log, return 3 is just log of empty list 3. Then, if we return the effect of that with the binding operation, we get the pure 3 back. And we concatenate the empty list with whatever string k1 returns. So we end up with the same exact string k1 had. At the end of the day, the whole thing on the left side of the equal sign is the same as directly applying the continuation function to 3, since concatenating an empty list with a list is the same as the original list. So we can run this. Very good. Okay, we have 1 law down, 2 to go. The next one is also super easy. Right identity. Binding an action M with return is the same as the original action. This is because the bind operator runs the effect and provides the result to the return, which in turn lifts the result back to the monad level without any effect. Let's see a few examples. Just 3 bind with return is the same as just 3, left arrow bind to return, etc. etc. So if we run this, all 3 should get returned true. Okay, good. So between the left and right identity laws, we have proven that the return function lifts values or functions to the monad level on both sides of the bind operator without changing the effects. Using the terminology we used for previous lessons, the return function should respect the monad structure. The third law is the associativity law. Much like the applicative's composition law, the associativity law ensures that monadic composition is associative. So, binding the first action with the result of binding the second and third action is the same as first binding the first and second action and then binding the third action. In practice, this means that we can regroup actions and nest binds in a way that makes sense to us and our software logic without changing the resulting effect of our value. Let's check if our instances follow this law. We chose just 5 as the first action. Then the 2 actions that will bind will be one that multiplies by 2 and one that adds 3. If this law holds, it means that we should get 5 times 2 plus 3 equals to 13, independently of how we regroup the actions. This law should also hold if any of the actions fail. We can check that by changing the result of any of the actions to nothing. Let's try like this first. So yes, it holds. Running the second and third and then the first with the result is the same as binding first and second and then the third. And if we change our second continuation function to a failure, it also returns true. The law holds in both cases. So we have a valid monad instance for the maybe type. Let's keep going. Here we can see that the either E instance also follows the associativity law in both cases. This is the same but with either. So first one holds, second one also holds. This means that we have a valid monad instance for the either E type. Not surprising, I know. What about our custom log type? Here we have the same action and functions but with log effects. As you can see, each action has a different log. Based on what we know, would the law hold? If we run this, we see that yes, it indeed holds. In both cases, the logs are in the correct order and the value is also 13. We can also see in the logs that the order the effects were run was correct. First 5 times 2 and then the result of that 10 plus 3. 13. And those are the 3 monadic laws. Way easier than applicative laws, right? With this, we covered everything needed to show our final definition of the monad type class. The monad type class is currently defined in the base library as this. A monad is an applicative with operations to embed pure expressions, return, and to sequentially compose 2 actions, both passing any value produced by the first as an argument to the second, the bind operator, and discarding any value produced by the first, the then operator. Instances of this type class also follow the left identity, right identity, and associativity laws. By the time you're watching this recording, this might or might not still be the definition in base. If the monad of no return proposal we discussed earlier or similar one is implemented, either or both of return and then might be removed from the monad type class. This doesn't mean that you shouldn't use them, since they will still likely be left somewhere as helper functions. But it does hint that the one thing unique to the monad type class is the bind operator. And that's it. You know everything you need to know about the monad type class. From now on, every time you see a type that is an instance of the monad type class, you only have to figure out the effect it represents. If you know that, you don't even need to know how it's implemented under the hood, because you already know the behaviors of all monads. The IO monad is a great example of this. We didn't explore how it works under the hood, but we can use its full power through the monad interface. Which reminds me of the do notation. If you recall lesson 10, we learned about basic AO and how Haskell provides the do notation as a syntactic sugar for expressions composed by the bind and then operators. Something like this. We have this scramble action with the start do block, and then each line that has this left arrow was a bind operator. And we can use this scramble, and it works. So this is just a refresher, but if you go to the lesson 10, you'll see like a full explanation of do notation. And everything you learn in that lesson about do notation applies not only to the IO monad, but to every type that implements the monad type class. That means that we can now do this, for example. Let's run it. This is the same function we wrote before. But since we created an instance of the monad class for log, we can now use do notation. We won't go into all examples and all details again, since you can see lesson 10 for that. And the lesson is already quite long, so let's finish here for now. And that's it for today. We haven't talked about all the functions you get for free when you create an instance of the monad type class. And that's because your homework is to go to the control.monad module in the base library and explore them. Take your time to understand and try all of them. In some cases, you'll see that a few functions are also constrained by other type classes that we haven't discussed. During this course, you have seen me go through over a dozen of type classes. You know how to do it. Try it yourself. I believe in you. Make sure to do your homework, and I will see you in the next one.